Let's now discuss the derivative and the tangent line problem. The goal for this lesson is to help you find the slope of the tangent line to a curve at a given point, and then use the definition of limit to find the derivative of a function, then understand the relationship between differentiability and continuity. Calculus grew out of four major problems that European mathematicians were working on during the 17th century. These are the tangent line problem, the velocity and acceleration problem, the minimum and maximum problem, and the area problem. Each of these problems involve the notion of a limit, and calculus can be introduced with any of the four problems. Now, what does it mean to say that a line is tangent to a curve at a point? Now, essentially, the problem of finding the tangent line at a point P boils down to the problem of finding the slope of the tangent line at point P. Now, you can approximate this slope by using a secant line through the point of tangency and another point on the curve. This delta x here is a small distance from this point here, so the second point is the point c plus delta x f of c plus delta x. So this is the secant line that we're going to use to approximate the tangent line at c at a point p equals x equals c. So if c, f of c is the point of tangency, and c plus delta x, f of c plus delta x is a second point on the graph of f, the slope of a secant line through the points is given by this formula here. You just have to substitute the formula. So from the formula for the slope, you just have to substitute. This would be your y sub 2, and then this is your y sub 1, and then x, this is your x sub 2, and this is your x sub 1, and then you substitute that. So the formula for the slope is just a change in y over the change in x. So the slope of the secant line is just given by this expression here. Or if you simplify the denominator will then just be equal to delta x. Now the right-hand side of this equation is called, this equation here is called, this part here is called the difference quotient. You have met this already in your pre-algebra class. And then the denominator here, this delta x here, is the change in x. So this numerator here, if you could see, is actually the change in y. Now you get a more and more accurate approximation of the slope of the tangent line by making this delta x close to 0, or making the second point very close to the point of tangency. So if you move this closer and closer to the point of tangency, or if you make your delta x goes to 0, your secant line would eventually coincide with the tangent line. And that is also the same true for this instance here. So if you make this delta x really close to 0, the point would go closer and closer to C, or to the point of tangency, until this secant line here would coincide with that tangent line. So that is how you're going to approximate the slope of the tangent line, by using the secant line. And so with that, we can define now the slope of the tangent line. So the slope of the tangent line is just the limit of the slope of the secant line as the denominator here, or as the change in x here, approaches to 0. The result that you get will be the slope of the tangent line to the graph of f at the point C, f of c. Now let's apply that definition to find the slope of the graph of f of x, which is equal to 2x minus 3 at x equals 2, or we say that c is equal to 2. So to do that, we have our c here, which is equal to 2. We'll just replace it. And then what we'll do is we will replace the x here by 2 plus delta x. So we have 2 times 2 plus delta x. Just replace x here by 2 plus delta x. And then you have minus 3, copy that minus 3. And then minus, so f of 2 means you replace x here by 2. So that's how you get 2 times 2 minus 3. And then you simplify it. So you distribute this inside the parentheses to remove the parentheses. So you have 4 plus 2 delta x minus 3, and then this is just equal to 4, so you have minus 4 plus 3. And then you combine all the constants. You have, so this would cancel with this, and then you have negative 3 plus 3, so this will just be 0. So therefore you have 2 delta x in the numerator, and then just copy delta x in the denominator. As you notice, the delta x will be a common factor, so that cancels out. Therefore, the limit of this expression here as delta x approaches to 0 is just equal to 2, because the limit of a constant is just equal to the constant. So therefore, the slope of the tangent line at x equals 2 or at c equals 2 is also equal to 2. Now notice that the limit definition of the slope of the function agrees with the definition of the slope of the line. So as you've noticed, the function given is just an equation of a line which has a slope of 2. And so therefore at x equals 2, the slope is just equal to 2. So just for the purpose of illustration, we've seen through using limit definition and through the definition of a line that both results agrees with each other. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. For vertical tangent lines, you can use the following definition. If f is continuous at c and the limit of f of c plus delta x minus f of c over delta x is either equal to infinity or negative infinity, then the line x equals c passing through this point c f of c is a vertical tangent line to the graph of f. For example, this function here, this has a vertical tangent line at c f of c. So this is how the vertical tangent line would look like. Now when the domain of f is a closed interval a, b, you can extend the definition of a vertical tangent line to include the endpoints by considering continuity and limits from the right for x equals a and from the left for x equals b. Now let's talk about the derivative of a function. Now the limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, which is differentiation. So what you see here is the formal definition of the derivative of the function at x. It is denoted by f prime of x, and this is just equal to the limit of f of x plus delta x minus f of x over delta x as delta x approaches to 0. Note that this expression here, or this f prime of x here, is a function of x. Now be sure to see that the derivative of a function of x is also a function of x. This new function gives the slope of a tangent line to the graph of f at any point, provided that the graph has a tangent line at that point. Now the derivative can also be used to determine the instantaneous rate of change, or simply rate of change, of one variable with respect to another. The process of finding the derivative of a function is called differentiation. a function is differentiable at x when its derivative exists, and it is differentiable on an open interval ab when it is differentiable at every point in the interval. Now, in addition to this, which is being read as f prime of x, the other notations that we use for the derivative of the function y equal to f of x is this one. So we also use dy over dx, or you have y prime or d dx. This is differentiating this function with respect to x, or you also use this. So these are all the notations that we use for derivatives. So this notation here is read as the derivative of y with respect to x, or simply dy dx. And using the limit notation, we can write dy dx equal to delta y over delta x as delta x approaches to 0. And or this is just equal to this one, this expression here. So f of x plus delta x minus f of x over delta x, and then take that limit as delta x approaches to 0, and they're all equal to the derivative of the function at x. Now let's find the derivative of the function using the limit definition. Suppose you're given the function x cubed plus 2x. Let's find the derivative of the function at any x, or at any point x. So by definition, this is just equal, f prime of x is just equal to f of x plus delta x. That means replace all the x's here by x plus delta x. And then minus, just copy this function here, divided by delta x. So this delta x replaced by x plus delta x, and then cube it. 2 times x plus delta x minus the quantity, this whole quantity here, divided by delta x. Then you expand this. When you expand that, that is equal to x cubed plus 3 times x squared delta x plus 3x times delta x squared, and then cube the last term times delta x cubed. Then this you distribute inside the parentheses, you have 2x plus 2 delta x. Then distribute the negative sign, you have minus 3x cubed minus 2x. Then you simplify. Notice that this would cancel with this, and then is negative 2x would also cancel with this one. So therefore, we have 3x squared delta x, just copy this and this and this over delta x. And then also notice that delta x is a common factor in the numerator. So therefore, you just have to factor out delta x and then cancel the common factor delta x from the numerator and denominator. Then after that, you just have to take the limit of this expression here. So when you take the limit of the remaining expression, this term just goes to 0. This one will just go to 0. So therefore, the limit of 3x squared plus 3x delta x plus delta x squared plus 2 is just equal to 3x squared plus 2. Now let's talk about differentiability and continuity. Now the alternative limit form of the derivative is useful in investigating the relationship between differentiability and continuity. The alternative form of the derivative of f at c is given by this expression here. So f prime at c means the derivative of the function evaluated at c. Now that is equal to f of c minus f of x minus f of c divided by x minus c, limit as x approaches c. This expression here is just the slope of the secant line. So if you look at this graph here, you have the point C, f of C, and then the next point is just x, f of x. To get the slope of the secant line, these two here, you just have to use the formula for the slope, the change in y. That's why you have f of x minus f of c over the change in x, so x minus c. And then what you want to do is just make, you just want to make this x goes close to c. That's why x approaches c. Note that the existence of the limit in this alternative form requires that the one-sided limits must exist and should be equal to each other. This expression here is called the derivative from the left. And this expression here is called the derivative from the right. Now it follows that f is differentiable on the closed interval AB if it is differentiable on the open interval AB, and when the derivative of the function exists from the right of A, and also the derivative exists from the left of B. Now, when a function is not continuous at c, therefore it is also not differentiable at x equals c. For instance, let's consider this greatest integer function, f of x equal to this symbol here. This is the symbol used to denote the greatest integer function. Note that this is not continuous at x equals 0. This is actually not continuous on all integers. Now, in here, since this is not continuous at x equals 0, it's not continuous, this greatest integer function is also not differentiable at x equals 0 because it is not continuous at x equals 0. And you can verify the derivative from the left is not the same as the derivative from the right of 0 is not the same as the derivative from the left. So we can verify that result by computing for the derivative from the left and from the right using the alternative definition. So if you evaluate this expression here and take the limit as x approaches 0 from the left, you get the derivative from the left. Now our f of x is just the greatest integer function. This is the notation for the greatest integer function. And then f at 0, so f evaluated at 0 is just 0. And take the limit. Now we take the limit. So when you say limit as x approaches 0 from the left, that means x is approaching 0 coming from the values to the left of 0. And those are the negative values. No? So in here, when we evaluate this greatest integer function, we're actually looking at the interval -1, 0, where 0 is not included. So what is the greatest integer on that interval? That is equal to -1. So therefore we have -1 for the numerator here, and then 0 negative, so 0 minus. Therefore that is equal to -1 over 0 minus is equal to positive infinity, because you have negative over negative, that's why it is positive. And if you have 1 over 0, that is infinity. So for the derivative from the left, we have infinity. Now for the derivative from the right, if you evaluate the limit here as x approaches 0 from the right, so we are now referring to the values of x that is approaching 0 coming from the right of 0. So those are like positive values. So if you evaluate this one, we're evaluating, if you evaluate or get the value for this greatest integer function here, you are looking at the interval starting at 0 up to 1, where 1 is not included. So what is the greatest integer there? That is 0. So the numerator is already absolutely equal to 0. So therefore, the derivative from the right is equal to 0. So in this case, the derivative does not exist because the left-hand derivative and the right-hand derivative are not equal. And although it is true that differentiability implies continuity, the converse is not true. That is, it is possible for a function to be continuous at x equals c and not differentiable at x equals c. To illustrate that, let us consider the given function here, f of x equal to the absolute value of x minus 2. If you look at the graph of this function, this is the graph of f of x equal to absolute value of x minus 2. Now in here we see that f is not differentiable at x equals 2 because the derivative from the left, the slope, from the left is actually negative 1. And the slope or the derivative from the right of 2 is equal to positive 1. So the derivative from the left and from the right are not equal. Now we can verify our result by computing for the derivative from the left and the derivative from the right. We do that by evaluating the one-sided limits here or using the alternative definition of derivative. So we take the limit of f of x minus f of 2 over x minus 2 as x approaches 2 from the left and from the right. Now our f of x is just equal to absolute value of x minus 2. And then at f of 2 is just equal to 0. Just evaluate this function at x equals 2, you get 0. And then to take the limit, we use the definition of this absolute value. Now, the definition of this absolute value at this interval here, when you say 2 from the left, you're looking at the interval less than 2. So x less than 2. Now, when x is less than 2, this absolute value expression can be replaced by the negative of x minus 2. So therefore, you can just cancel x minus 2 because that will be a common expression, both numerator and denominator. And then you will then be left with negative 1. So the left-hand derivative or the derivative from the left is negative 1. Now for the derivative from the right or for this right-hand limit, this expression may be replaced or can be replaced by x minus 2. So therefore, you just have x minus 2 over x minus 2 in this case because you have 2 from the right, that is x greater than 2. So therefore, if you cancel x minus 2, you have 1. So the limit is just equal to 1. As you see here, the derivatives from the left is not the same as the derivative from the right. So if f is not differentiable at x equals 2, and the graph of f does not have a tangent line at the point 2, 0. So we say here, this is an example of a function which is continuous, but not continuous at a point, but not differentiable at that point. Now, in our previous example, we have shown that a function is not differentiable at a point at which its graph has a sharp turn or a vertical tangent line. Now also, differentiability implies continuity, and it is formally stated in Theorem 2.1. If f is differentiable at x equals c, then f is continuous at x equals c. Now the relationship between continuity and differentiability is summarized here. We have seen that if a function is differentiable at x equals c, then it is continuous at x equals c. So therefore, differentiability implies continuity. But the converse is not true. Continuity does not imply differentiability. It is possible for a function to be continuous at x equals c and not be differentiable at that point.